So dear participants, in our last lecture we had got pretty long discussions on the notations of timers that are used in various PLCs. We have seen what are the different timing operations that are available with PLCs, and in this lecture I was supposed to continue with the operational aspects of timers. We will talk a bit on the sequencing operation. We will see that how cascading operation takes place with the timers. But before that, what I wanted to show you that the operation of an actual timer. Let us go for that. I will be using this Delta software to show you, just demonstrate the basic operation of timer. Okay, a very simple one. We will start the new one. We will give the title of timer, since it is going to be a timer operation. We will get into the simulator mode straight away, and we will put here one device that is an NO contact, and I will directly connect an application block to this NO contact. Now, while the application block has been chosen, they have asked me to choose the particular function that I am going to get out of that application block. You can see that so much functions are possible with this SB2 PLC of Delta. So it is never necessary to think that PLCs are just devices with DI and DIOs. Definitely that are the most extensive application where PLCs do find in industrial realm, but capacity of PLCs is very high. We will choose here timer, and you can see the application number is 96 and the application name is timer that we have come to know. Now, in order to know a bit more about the timer, you can click this block. You can see that this is a 16-bit register. The timer is actually a 16-bit register where 8 bits, the upper 8 bits that given you the number of the timer, and the lower 8 bits that gives you actually the value that you are putting as preset in the timer. So you can see also the device range. Since we are using SB2 series of PLC, you can see this is SB2 series. This SB2 series, there is the timer block. You can see there are T0 to T255, that there are in all 256 timers, and different time bases are there. This is 100 millisecond time base, 10 millisecond time base, and 1 millisecond time base. With certain conditions we can achieve these different time bases. Definitely if you want a 10 millisecond time base, you can simply choose T200. You need a 1 millisecond time base, you can choose any value between T246 to T49, like that. For our particular operation we will choose 100 millisecond time base because we want just to demonstrate the function, and I will be choosing timer T0. Okay, so you see here the S1 I will choose timer, the address value is 0. For S2 I will be choosing K, and since this is a 100 millisecond time base, we will go for 5-second delay. So for 5-second delay we need the value of 50 here. Okay, so I will make it 50. Okay, so now you have got this timer block with the value of 50. You can also find that you can change it from here also. There is no problem, you can change simply the value. Okay, so now I will take here one contact, but this contact will be the contact of the timer coil. So I will put here again one normal open contact. This is a T, the range is T0 to T255. You have already seen the device number is 0 because we are using the timer T0, so the contacts will be that of T0 also. And finally here we will be putting the output coil, that is Y0. Okay, so this is our basic and very simple program. The program is meant to work in a manner that whenever I will be putting this rung condition true, that means I will set this switch on, then the timer will start counting. It will count up to 5 seconds, because 50 into 100 millisecond is equal to 5000 millisecond. It will get up to 5 seconds, and once this 5-second time is over, then this contact will be changing its state, because right now it is an open contact, it will be closed, and your output whatever is, it will be energized. This is the simple operation. So let us compile our code. It is compiled. Now let us download it to the PLC. It is done. Let us get into online mode and then let us run the PLC. So now you can see this K 0. K, the present value is 0. Okay, now I will set this on. The moment it is set on, you can see the K starts counting. So this is accumulating the value. Now once it is over, once this 50 is reached, then you can see this is energized. So once this 50 is reached, the timer coil, it changes its state and your output is energized. So this is the thing, this is the basic thing how a timer actually works in a PLC. We will make some changes. We would like to make some changes. For that I will get back from online mode. I will stop the PLC and I will try to make some changes in the program. Here I will be putting one block here. Okay, fine. I will delete this. I will give here one output. Let this output be here. This I will not use. This I will also not use, and here I will be getting this branch. Okay, and here at this point I will be introducing one NO contact. This NO contact I will write as T0, because here I will be putting this timer block. So here the application is a basic instruction in which I am to go for this timer, and this timer will be having its address 0 because I have taken timer T0. I will be taking the value of K, and again I will put here 50. This is a timer with 100 millisecond base. So now this is the program, and let us see what is actually happening here. Okay, you can see that this is the normal contact terminal of this timer. This is the NC. Okay, so let us see what is now happening. We will compile it. We will get into online mode. Oh, sorry, we will get it to the PLC. Okay, I had started the online mode, I think. That's why it is somewhat problematic. Fine, this online mode is there. Then let us run the PLC. Okay, so now you can see that when I put this on, you can see this output is on. But till what limit the output will on, let us see. You can see the output will remain on till it reaches 50. So in earlier case, what we had seen? We had seen that actually the output goes on. The output goes on after a certain delay. The output goes on after a certain delay. So that was an on delay timer. But here what we have done? Here we have seen that the output goes on when we switch on the NO terminal, that is this X terminal, our input. When we energize the input, the output is on, and it is on for a certain duration. So this becomes your simple interval timer. So like that you can definitely design your timer for certain timing application. Then I keep this particular problem for your mind, that how to generate an off delay. You put it off. After that your timer your output device should remain energized for the preset duration of time. Now another thing that I wanted to show you, I will put this off. I will again put it on. You can see here, if at this point of time I put it off, then you can see your timer goes to 0. So that means that there your timer is not able to memorize the thing, that how much count it has already carried out. It is unable to keep that in its mind. So this is another point that you need to remember about the timers. The timers which are unable to keep track of the time, whenever there is a power failure or some other operation or the particular situation at the input that goes wrong, it does not hold the time. Such type of timers are called non-retentive timers. Non-retentive timers, that means they do not retain the value. The timers which can remember that particular value at which the input condition of the rung was wrong or there was some power failure, we call it to be a retentive timer. So let us now get back to our actual discussion. Okay. Now we will see what is basically sequencing operation that it can be achieved using on delay timers. Sequencing operation, the name itself suggests that something will be working in sequence. Now you can see in this particular ladder diagram, the output, this is one coil. So this coil is energized by this input. So this coil is having its contacts in the second rung, and then this second rung is having that delay timer block, that is the on delay timer block, and which is giving its output, where that is connected to Q, that is the output terminal of this timer. Now you can see, if we consider this figure, when IN, that is input 1, is switched on, the contacts they are associated with the output, they actually start the timer. You try to grasp the particular condition. You have put this contact on. When you have put this contact on, your coil is energized. Since your coil is energized, the NO contact which is associated with this output, that actually triggers the timer. So the timer will run for the preset timing. Here the preset is 5.5 second. So after this 5.5 second is over, your output 2 is switched on. Now you can see, following the input in 1, output 1 is switched on, and followed by 5.5 second later by output 2. You just think of two LEDs here. If you connect one LED at this coil and another LED at this coil, then very simply you can find that whenever you put the switch on, one of the LEDs will be glowing immediately. After 5.5 seconds, another LED will be glowing. So if you need some sort of sequence operation to be performed during a process, then you can definitely use on delay timers in the fashion that I have already just shown to you. Next comes the cascaded operation using on delay timers. Using cascaded operation, you can generate very long durations, very long delay values. Now you can see this cascade operation is nothing but cascading or linking one timer after another. You are actually linking one timer after another. You can see this is timer 1. The contact of the timer 1 is given to timer 2. The contact of timer 2 is given to the output. So when you put this switch on, this timer is activated. Once this timer is activated, and here you can see that this is there with Mitsubishi notation, where input is given as X400 and your output is given as Y430. That this is the address of the input and this is the address of the output. Now you can see the timer that we are using particularly is T450. T450 is the number of the timer or address of the timer, and in the first case we are giving a delay of 999 second. So once you put it on, once you set on X400 input, then what will happen? That this timer will be activated. So once this timer will be activated, it will start counting. It will start counting and it will count up to 999. Once this 999 second is over, the associated contacts with this timer that will get activated. So once this is activated, it will energize the second timer. In case of second timer, you can see that the second timer is programmed for a delay of 100 second. So once again this 100 second is over, then it will actuate the associated contacts of the second timer, because you can see this timer is T450 and this is T450. This contact is T450. So this contact is associated with this timer coil and this contact is associated with this timer coil. And finally your output Y430 is associated with the contact of the second timer. So once you put this on, first of all this timer will count the total time from 0 to 999. Once the count is over, this 450, this terminal will be activated. When this terminal will go from off to on condition, then this timer will start accumulating the count, and accumulating the count means it will start counting the time, and once this 100 second is over, then this particular terminal will become closed. Since this terminal is associated with the timer T451, this is the terminal 451, and once this terminal is closed, then your output will be activated. So here you can see you have given the input signal. Throughout you are keeping your input signal on, because if you put off the input signal in between, then your entire timer operation is lost and you are again reset at zero condition, because these type of timers are non-retentive timers. Now you can see that here in the first case there is a 999 second delay, and after that this timer gives the output. So this is the timer 1, that is T450. Now once this timer gives the output, your second timer starts operating, and after 100 second, because in second timer you have got a delay of 100 second, after 100 second this timer will give the output. The moment this timer will give the output, the associated contacts T451 will become high, and when this T451 will become high, your output will be energized, and your output is given as Y430, it will be energized. So now you can see that with this type of timer you can generate 999 plus 100, that much amount of delay. So if you need a very longer delay which is not available directly with the timers that are contained in that PLC, you can definitely cascade the timers to get a longer duration of delay. Now how you can obtain on-off cycle using timer, that is also very interesting. Here you can see at the output you are getting the pulses. You can see that the output you are getting pulse. Okay, how it is possible? Let us try to find. You can see here that what we have done, this is one input which is generic type, normal open contact, and here we have connected the NC, normally closed switch. But this normal closed switch is not an external connection. You can see this is of an internal relay. Please remember that in unit 1 we had a pretty long discussion about these internal relays. They are virtual relays. They can be used within the program. However, they are not connected with any of the output terminals. हार्डवेयर आउटपुट टर्मिनल्स के साथ इस रिले की कोई संबंध नहीं रहता है. Now you can see here we have used the normally closed terminal, this IR1, and this is the coil actually IR1 that we have connected to the Q output of timer 2. Q output of timer 2, I have connected this internal relay. Now in the first rung there is T1 timer, which is again a T-on timer. In this case we have given a delay of 5 seconds, and in case of the second timer also we have given a delay of 5 seconds. Now you see that the second timer is energized or triggered by the first timer very simply, because here there is the output and we are trying to get a pulsing pulses at the output, and whatever the coil is associated or the contact is associated with timer 1, that is the trigger point for timer 2. This particular thing you be very careful. In rung 1 we have got one input, this is an external input. Then there is one NC contact which is the contact of internal relay that is connected to the output of timer 2 which is present in the second rung, and this timer 2 is triggered by the contact of timer 1. And which contact? It is a normal open contact, because since ultimately your timer on is going to have a relay at its output, virtually there will be relay at its output, so relay will be having two contacts, one T1 and other T1 not, that means the reverse contact. So here you can see this is the NO contact, we have not connected here the NC contact, this is simply NO contact, And now try to find what is happening. Whenever you are putting this on, that is you are setting this switch from off to on. So when this is put on, this connection is already established over here because this is an NC connection. So your timer will be triggered, and after 5 seconds, this T1 contact will be closed. When this T1 contact will be closed, what will happen? When this T1 contact will be closed, this timer will start counting. Once this timer will start counting, after 5 seconds, this IR1 will be activated. When IR1 will be activated, then this IR1 NC contact will become NO. So now you see, earlier this was NC. When this was NC, after 5 seconds, the output was high when you have applied the signal. Now what is going to happen? That after 5 seconds, this has become high. When this has become high, this particular I should say timer, that will start counting for 5 seconds. Once this 5 seconds is over, this will become of opposite state. So this is NC, now it will become NO. When this is becoming NO, this will be deactivated. So now your output is low. Once your output is low, this T1 definitely at the same time it will also become low. The moment it is low, this IR1 is going to be low after 5 seconds. Okay, so no, the IR1 will be low immediately because there is no connection. Since there is no signal, this will become low. The moment IR1 is low, then your this particular contact that is associated with IR1, earlier it was NO, now this will become NC. So this is very simple an operation. Okay, so in this way you can generate on off cycle using on delay timers. And we have shown here this I'm sorry, this is not Mitsubishi notation, this is Siemens notation. There is wrong, I think this is a typo or copy paste problem. Please remember this is a Siemens notation. Anyway, be very sure about the operation. I will again brief it. Initially you see that this is not activated, your output is not activated, it is low. And since your output is low, definitely you are having a low signal at the output, no problem. Now you apply the signal in. You do not put it off, you applied the signal here. That means this open switch becomes closed. Once this open switch is closed, your timer will get the trigger. Once the timer is triggered, after 5 seconds, it will be on. Now, once this is on, your output is going to be high. Now point is, for what duration it will remain high? You can see, once this is high, that means the timer job is over for after 5 seconds. Then this particular contact which is associated with this timer, that will go from NO to NC. It will be closed. Once it will be closed, this particular timer, that is T2, will get trigger. Once this is trigger, it will count 5 seconds. So this will be on for 5 seconds. So after this 5 seconds, IR1 will be activated. When this IR1 is activated, then the NC contact which is associated with IR1, that will become NO. So when this will become NO, this particular timer will get no more signal, so the output will be off. So here you can see the output is off. So for what duration the output will remain off? The output will remain off for 5 seconds. So once the 5 seconds is over, then this particular output, that will again become deactivated. When this is deactivated, this NO will become NC, its normal condition. Again you will getting the output, and this cycle will go on till the input signal is there. So this is very basic on off cycle timer that you can design using on delay timer. Okay. Now let us see what is off delay timer in PLC. I am not going to explain too much right now because you know already the on delay timers, the off delay timers, only the operation is different. rather the symbols are same, therefore we are going only for Allen Bradley RS Logic's notation. This is timer which is off delay type. The timer address is 4.1. The time base is 1 second. The preset is 5. That means the timer will count up to 5 seconds. And your accumulator at the initial point, it will be 0. It will be 0. And once the time starts, the accumulator will increase like 0, 1, 2, 3, 4, 5. Okay. So here we can connect the input. There is one enable bit and there is one done bit. You can see here what we have done. We have connected this done bit in the second run. That means the NO contact, normal open contact associated with the done bit is there in the second rung, which is connected to the output coil. Now you can see when we give the input, for the entire duration for which input is there, the enable terminal will be on. Very simply, there is one TT terminal also. The TT terminal for the entire duration it will remain off. But now after the time this enable period is over, after this enable period is over, the TT terminal will remain on for the delay time. The TT terminal will remain on for the delay time. And the done bit, you can see the done bit is most important. The done bit will get on. The done bit will get on once your input signal is there, and it will be retained on even after there is no input. This input, I am talking only about the signal input. Many a times people confuse, if there is no power, then how will the timer work? I am not talking of the power, I am talking of the signal input. Power has definitely to be supplied. Without power, no operation is possible. So power supply will be throughout. However, this input terminal will be absent. So once the input terminal is absent, for the entire duration for which TT is high, then this done bit will remain high for this entire period, right from starting to the end of the TT period. So this is the operation of an off delay timer. And you can see this is further detailing of the off delay timer. You can see here, this is the off delay timer. There is one enable bit, there is one done bit, accumulator is there, the time base is 1, preset is 10, so the delay that is expected is 10 seconds. So you can see here that a very short pulse is given at the input. This is the input. So for that short duration, the enable will remain high. Now you can see that the done bit, how it will behave? It will start at the same point as with the enable bit or the trigger bit, that is the input bit. It will become 1 from 0. Now it will be retaining its condition for this entire 10 second. For this entire 10 second after your signal is put off. Now you can see here at this point your signal is going from state 1 to state 0. So after your signal becomes 0, after that 10 seconds will be maintained at the done bit. So now it is very sure, you can see here the enable bit is connected to output 01301. So this output 01301 will be remaining high for the entire period only during which the enable terminal is high. So you can see here the enable terminal is high, and this T4.1 enable terminal is associated with this contact. Therefore this particular coil will remain high only for the enable duration. After that you can see in rung 3 we have got the TT terminal. You can see here this will remain high for the entire period of operation, that is the enable period plus the delay period. Then you can see here actually you first consider the rung 5. Here we have used the done bit. Now you can see what will happen with the done bit. Okay, here this output. So the done bit will remain high for the entire operation. Okay, and then it will go low. So here you can find that this particular contact which is associated with the done bit, it will remain high for the entire period. Once this done bit is over, it will go low, and this is the reverse done bit, that is the NC of the done bit is connected here, then it will work just as the opposite of rung 5. So rung 4 and rung 5, they will act just in reverse manner or opposite manner, as they are NC and NO of the same operation that is associated with the contact, that is the done bit. Okay, so this is application of off delay timer. Now there is as I have told you that there is a concept of retentive timers in PLC also. The retentive timer operates the same as an T-on timer. However, the accumulator is not reset. This is the important concept. The accumulator is not reset when the timer enable goes to 0 and continues to increment whenever the enable bit goes to 1. इसका मतलब क्या हो गया कि अगर किसी कारण में आपका ट्रिगर इनपुट जो है, जो एनेबल इनपुट जो है, जहां पे आप लोग इन दे रहे हैं सिग्नल या EN एनेबल सिग्नल दे रहे हैं, वो सिग्नल अगर किसी कारण 0 हो गया, एक्यूमुलेटर अपने काउंट को याद में रखता है. सो देयर इज अ मेमोरी which retains the value. When the accumulator bit reaches the preset value, the timer timing bit goes 0 and the done bit to 1, and the accumulator bit remains in that state until a reset instruction is received. आपने थोड़ी देर पहले डेल्टा PLC का प्रोग्रामिंग में देखा, the moment count is over, खत्म हो जाता है, काउंट में क्या रहता है, फाइनली इट रिमेन्स दैट वैल्यू, प्रीसेट वैल्यू वहां पे बैठ के रह जाता है 50. सो हियर आल्सो द सेम थिंग हैपेंस. जब काउंटिंग खत्म हो जाता है तो एक्यूमुलेटर में फाइनल वैल्यू इज रिटेन्ड. In any case, the final value is retained in accumulator. However, in between, if at certain condition the signal value is absent, the accumulator will not lose its condition. It will retain the condition very simply. Okay, it will hold that situation. कहाँ तक काउंट हुआ था वो होल्ड करके रखेगा, ताकि सिग्नल वापस मिलने के बाद वो फिर से चालू कर देगा उसी पॉइंट से. 0 से फिर से चालू करने की जरूरत नहीं पड़ेगी उसको. अदरवाइज दूसरे में क्या होता है कि नॉन रिटेंटिव टाइमर अगर रहा, अगर सिग्नल आपने हटा लिए तो टाइमर इमीडिएटली बंद हो जाता है, इट बिकम्स 0. अगेन जब आप सिग्नल अप्लाई करते हो तो आपकी टाइमर आगे बढ़ना शुरू हो जाता है. Now you can see here, this is the retentive operation in Allen Bradley PLC. This is RTO. RTO means retentive timer, O means on. This you can see timer address is 4.2, time base is 1, preset is 100. That means it will count up to 100 second. Okay, now you can see there very simply there is enable bit, there is done bit, and we have connected the done bit to the output. Now you can see here we have given an input signal for this much duration. So the particular duration for which there is an input signal, definitely there will be the enable signal present, because the enable signal will remain activated till there is the input signal. So the enabled signal will remain activated. Now you can see the accumulator has started counting. You can find at this point the enable signal is absent. For some period the enable signal has remained absent, but the accumulator has retained its value. Again, when the enable signal is given, the accumulator has started counting and it will go up to the preset value. Now you can see how the TT will behave. TT is also present here. For the total time the accumulator is counting, the TT will remain high. And what about the done bit? You can see the done bit will be remaining high after the preset time is over. Otherwise the done bit is low. If at any moment of time we trigger the reset input, there is all one reset input. If we trigger it, then whatever your accumulator content it becomes 0. So this is the basic operation of a retentive timer, and I hope that things are now clear to you. Thank you. In our next lecture we will go for further applications of timers that are available with PLCs.